Hello, welcome to Advanced Algebra 2. We're looking at a couple things today. One of them is kind of fun. It's a little sketchy. It's called Functions in the Real World. And then the other one that is coming up is just kind of a bunch of different graphs of functions listed out for you, kind of making a toolbox. Speaking of toolbox, I think that's the word that they used in physics last year. If you're a sophomore and you had physics last year. And in fact, what we're doing now, called Functions in the Real World, is in fact kind of like some of the graphing you did earliest in physics. We got some examples. You're going to see a few different things happening, and then hopefully when you come back to class, knowing kind of what your options are, you'll be able to apply that to the different type of story problems you see. So the first example. The number of used aluminum cans you collect and the number of dollars refunded to you are related. Sketch a reasonable graph. I told you it was sketchy. So first of all, you need to label axes. First one would be, there we go. Number of cans recycled versus money refunded. And then you'd have a line going up. You'd probably start at 0, 0. And I wrote in parentheses, line should be straight. When I draw things for you on a whiteboard or on paper, I work incredibly hard to make them straight, and I would like you to use a straight edge, please. It is, unfortunately, impossible to draw a straight line on an iPad screen. So I apologize that it doesn't look straight, and I'm yet telling you you need to draw it straight. It's a limitation of the tool at the moment for doing this. All right, next example. Here we have Katie. Katie comes home from abroad with a new and highly contagious disease. In the ensuing epidemic, which sweeps through her city, the number of people who have the disease at any one time related to the number of days since Katie has arrived in town. Sketch a reasonable graph. So, need some axes. X-axis, independent axis, would be number of days since return. The dependent axis, number of people with disease, because you know that the number of people depends on how long since she's been back. And then the graph starts low and starts at 1 because Katie had the disease, and it increases. And it does kind of taper off, though. It's highly contagious, and so it's exciting that more people get it. But then eventually it slows down, and the reason why is you run out of people to get the disease, because eventually everyone has the disease. Now, when the graph turns and flattens out like that and won't go past a certain point, that is called an asymptote. And that's important as a concept for us this year. It'll pop up here and there, and I'll point it out when we get there. But in this case, the number of people with the disease cannot go past the town's population. So here the green line, which is intended to be horizontal, would represent the town's population. All right, example the third. As you play with the yo-yo, the number of seconds that have passed and the yo-yo's distance from the floor are related. So some axes. Number of seconds would be on the x-axis. Distance from the floor would be on the y-axis. And ga-boing, 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 your yo-yo goes up and down. And those are intended to be peaks and valleys that are about the same height and about the same depth, because your yo-yo would go up and down the same height-ish, depending on how good you are at holding your hand in the same spot, so forth. Now, a function like this, or a graph like this, which kind of goes back and forth following a pattern, repeating itself, is called a periodic function. And it's called a periodic function simply because it repeats itself over and over again. It's a key term. It's going to come up eventually. Don't let it bother you too much, but understand that this yo-yo situation is different from the disease people situation and different from making money off of aluminum cans. Those are these 3 examples. It's good to have a different view of different things. The real work will come, though, when you're trying your own, for the follow-through assignment. We will actually do these type of things for several days, as a part of the assignment. There's overkill for doing too much at once, but it's also good to come back to it, just a few each time. Okay, that's one part. Now, that was the fast part by far. Excuse me. The next part though, is more work, and it's going to start out boring, but it's going to end really, really awesome, at least for me. Okay, so common math functions. Quick reminder of what a function is. It's a connection between the domain and the range that has only one output for each input. And the important thing for us is on a graph, a function always passes the vertical line test. And that says, no vertical line can cross the graph more than once. So for what we're doing today, everything is a function. In class, as some practice problems at some point, you'll be asked to tell between things that are and are not functions. You will enjoy those problems because they are significantly easier than the other problems. All right, so we've got some these families of functions we need to know. We're going to come back later and do similar things with them, but you got to know who belongs to which family. So first of all, a linear function, y equals x. Now, I got to tell you, making a t-chart for y equals x is quite possibly the least exciting thing you could do with your life. You put some x's down, you put some y's down. They are the same things as the x's. So, yeah, I apologize. You just lost 20 seconds of your life. But still, you got to get it down. So you throw some dots down. But before you do that, you need to scale your axes. And since we're only going fives, I just went by ones to make it all work out happy, go lucky style. Throw some dots. Doom. Connect the dots because there's no magic reason why just those numbers are the ones that could work. Put some arrows on the end. Boom, linear function. You should be thoroughly unimpressed. I mean, it's a linear, it's y equals x. It's a line, 45 degrees. Slope is 1. The y-intercept is 0. Can't even be bothered to move up or down. Yet. Now, next one. Absolute value. It's possible you've graphed this before. It's also possible you have not. Still not very hard. Go ahead and make yourself a t-chart, x's and y's, and I did the same x's, -5 to 5, but the y's are almost the same, but not quite, because here we're talking about things where when the x was negative, the y made it positive anyway, because of the absolute value. Okay, boom, boom, boom. Throw some axes down, still talking about relatively small numbers, so I went by ones. And then making the dots here, boom, chicka-boom, chicka-boom, boom, boom. And then it's a V shape. Pretty awesome. Still goes forever both ways, but a V shape. Huh, okay. That's a little bit different than the linear one. Still not terribly exciting. Still not hard. But, it's a thing. Now, I will say this. Both the linear one and this absolute value one, they should look like straight lines. So hopefully you're drawing them with a straight edge. I'm going to need that from you. Again, I can't actually do a perfectly straight line on the iPad because of the way the tool works. Sorry. Okay, moving on. Quadratic function, y equals x squared. You've all graphed a few of these before in your life. Throw down a t-chart. Still went from -5 to 5 on the x's. The y's are the squares, so they're always positive. And they do get kind of big near the 5's. So in terms of scaling, I went by 5's on the y's. You could probably get away with going by like 4's and 3's, but I like to go by 1's, 2's, 5's, and 10's. It's a good, clean way at looking at numbers. Not absolutely mandatory. Certainly not in Advanced Algebra 2, but realistically, it's just a good habit to get into if you're curious. All right, the x's can still go by 1's because we're still choosing numbers between -5 and 5. Plot the dots, connect it up. It's a UE. I went super fast on that dotting because you should have graphed many parabolas before by now. There's still arrows on the ends because they go forever. All right, moving on. Cubic function. This one you might not have. And I apologize about the page number thing listed on the screen. Couldn't get rid of it. Okay. Now, again, went ahead and made a t-chart. Got x's and y's. Boom, boom, boom. Same x's as before. This time the y's kind of go crazy. All the way down to -125. and all the way up on the positive side to positive 125. So when you make your scale, the x's can still go by ones. I went by tens on the y's. You could do something different if you want. That still won't get me all the way up to 125, but it will get me really most of the information that's going on here. Make the dots, boom, boom, boom. And now it's kind of like a parabola on the right half, but the left half is kind of like an upside down parabola. But the truth is they actually both grow faster. Actually, they grow faster after 1, before 1. This one grows slower, but don't worry about that. They grow faster, or it goes down faster. Okay, next one. Square root function. Now here, x and y's, got a t-chart action. This time I listed all the x's first because something strange is going to happen. When you try to stick the negative x's in, you get a failure. So hopefully you didn't even try too hard, because the negative x's are not in the domain. You can't do a square root of a negative number. You can try really hard. I suppose if you have a good imagination, you can do a square root of a negative number. But that's actually a joke about imaginary numbers, which you're not supposed to know about yet. So it probably wasn't a good joke. All right. However, starting at 0, certainly you can get some values. Now, the problem is the actual values are kind of crummy for most of the numbers, right? It's like 0, 0, good enough. 1 is 1, good enough. 2 is 1.4, 3 is 1.7, 4 is 2, 4, 2, that's nice. 5 is 2.2-ish or something like that. I don't know. They're not exciting numbers. So I went by ones on the x's. Oh, and excuse me, I didn't even show it, but on the y's, went by ones also. I'll go ahead and fix that here. We'll go, oops, wrong color. Went by ones on the y's, so you look at that. Now it looks like I know what I'm doing. Hey, went by ones on the y's, went by ones on the x's, and zoom. For what it's worth, that is exactly the top half of a sideways parabola. If that sounds like an interesting thing to think about, great. You're welcome. If you're thinking, don't worry about it. Not a big deal for now. All right, next one. Cube root graph. Now this is the cube root x. Again, XY chart, but in this case, I only chose the x's that were going to give me pretty y values. Nice integers for y values. So -8, -1, 0, 1, and 8. Now, again, I could have kept going. -27 and 27 would have been the next ones. -64 and 64 would have been the next ones, but I just wasn't that motivated. Okay, so go by ones. I still went by ones on the y's. You could get all excited and go by halves or tenths, probably. Well, not really tenths, but by halves or quarters if you wanted. I just like to go by ones. We'll see. And then, zoom, that's your cube root graph. Wait, nope, I fixed it a little bit. There we go. This is sort of a mirror image of that cube graph from a couple graphs ago. So if you want to go compare with that one and see how they're kind of similar, but this one's sort of sideways, but not exactly sideways, might be interesting. There's something cool there that I'm not going to talk about now, but there's some interesting connection there. All right. Now we're going to have fun. Oh, this last one. This is awesome. Okay. This is y equals x. There's a funny thing that looks like maybe around that x, there's like something like jail bars with like little things going into the ground to stop the x from digging his way out or something like that. It's an actual thing. I didn't make it up. It's called the greatest integer function. But calling something the greatest integer function becomes tiresome for people who know the lingo and feel cool. So we call it the floor function. It's technically the greatest integer function, but every math person knows that means floor. And okay, this is just so awesome. Not going to do a t-chart because the interesting things happen at the integers, but even more interesting is the nothing that happens between the integers. Okay, so let's bear with me a little bit. scale it out. Just go by ones, up and down, left and right, everywhere. That part should not be scary. Okay. This is awesome. Okay. Now, let's get started. 0, 0. Everybody likes 0, 0. See the dot at the origin? Great. Now, what's going to happen here is, for every x value, the y value is the biggest integer that is less than or equal to the x value. I'm going to say it again, and if you haven't had enough, you can go back and forth on the video. The y value is the greatest integer that is less than or equal to the x value. So, looking at that x at 0, 0, as I move my way over on the x's toward 1, the y values stay at 0. Except when I get to 1, that's no longer true. So there's an open dot at 1. Now what happens next is super awesome. At 1, the greatest integer that is less than or equal to 1 is 1. So, boom. At 1, you have 1. And then as you work your way to the right of 1, meaning numbers slightly more than 1, but less than 2, the greatest integer that is less than or equal to those numbers is still 1. Until you get at 2, and then it'll change. So we put an open dot at 1. At 2, the greatest integer that is less than or equal to 2 is 2. And that stays true as you move above 2 until you get to 3, in which case the value is 3. And that stays the case until you get to 4, at which case the value is 4. True until you get to 5, at which case the value is 5, etc. Whoa, now that got exciting. Etc., etc. Let me go back just a little bit here. Sorry, folks. All right, now, 5, boom. Now, going back to the left side. For all the numbers between -1 and 0, the greatest integer that is less than or equal to them is -1. Until you get below -1, and then it's -2. Until you get below -2, and then it's -3, etc., etc. Or you can see that the pattern just continues. Now, I got like a dotted arrow thing going on here to show that the pattern continues, not, oh, and then it takes off into a line going straight up, because that's ridiculous. A lot of people look at this and go, hey, that looks like a set of stairs. So in fact, we often call this look of a thing a step function. And I want you to try to understand what a step function looks like. And, you know, if it's a step function looks like the thing where, like, it's broken everywhere and it kind of follows the same thing and they're all little flat stairs, that's almost something. We can put that together and make it work. Hey, this is almost it. What else we got? Oh, the assignment. That's not on your page because I simply could not fit that line of text on the page. And I didn't want to waste another piece of paper just to show you what your assignment would be when you come back. But hey, we're done. So thank you for watching. Please let me know what your questions are when you come back to class. And, you know, I hope you had a good time.